Okay, all right, so this is section 2.5, zeros of polynomial functions. I am live here with block 4. Block 4, do you want to give a shout out? Hi. Okay, so recall that an nth degree polynomial can have at most n real zeros, but in the complex number system we can say that every nth degree polynomial function has exactly n zeros. So I'm going to underline that important part or highlight that for you. That is that every nth degree polynomial function has exactly n zeros. All right, and that means that if we were going to say, oh, I've got f of x equaling, 5x to the 6th minus 3x to the 4th plus 2, this function is guaranteed to have how many zeros? 6. So it's going to be guaranteed to have 6 zeros. They may be real, they may be imaginary, they may be repeated, but there's going to be 6 of them. Everybody understand that? Yeah. Okay, so that leads us to the fundamental theorem of algebra. You don't need to write this down. If f of x is a polynomial of degree n, where n is greater than 0, then f has at least 1 0 in the complex number system. Well, I personally think that this is not nearly as interesting as what we just talked about, because at least 1 is not very specific. What we want to know is exactly how many there are, okay? And so if it's a degree 4, there's going to be 4. If it's a degree 8, there's going to be 8. Again, they might be real, they might be imaginary, they might be repeated, but there's going to be that number. All right, that leads us to the linear factorization theorem, which says if f of x is a polynomial of degree n, where n is greater than 0, then that function f is going to have precisely n linear factors, which makes sense because if it's degree n, it's going to have n zeros. So to get the factors, you would just do x minus each 0. Make sense? So for example, let's do a quick example here. Oh, by the way, the n factors would look like this. So I could write this as a times x minus c sub 1 times x minus c sub 2 and so on, all the way down to x minus c sub n. In other words, n linear factors. All right? So C1, C2, and Cn, all those would be complex numbers. Remember, complex numbers could be imaginary, like 2 plus 3i, but complex numbers are also real, right? Like 5 plus 0i is just 5, right? So every number you've ever worked with in your whole life is a complex number. It's just you never knew that there was a plus 0i after it. Everybody with me? Mm-hmm. Okay, so here's a quick example of a function. Let's say I had x squared minus 9. I know that I can factor that into linear factors. What would that factor into? X minus 3, x plus 3. And I also know that the zeros would be 3 and negative 3. Are we okay with this? What was the degree? How many zeros did we get? 2. How many linear factors did we get? 2. All right. So what about if I have this example? Let's say I have x squared plus 9. If I want to find the zeros, I would just set my function equal to 0. So x squared plus 9 equals 0. Maybe I would subtract 9 from both sides. I get x squared equals negative 9. Then what? Take the square root. Don't forget the plus or minus. So I would get x equals plus or minus what? Hands, please. Tiger?
3i.
Plus or minus 3i. So this guy does have 2 zeros. The zeros would be 3i and negative 3i. Everybody with me? Yes. What was the degree? 2. How many zeros did we get? 2. Remember, they might be real. They might be imaginary. They might be repeated, but there's going to be 2 for every degree 2 polynomial function. Are we okay with this? Yeah. And using this linear factorization theorem, I could write this in factored form by writing what? Hands, please.
X plus 3i and x minus 3i.
All right, x plus 3i times x minus 3i. Are we okay with this? Yeah. All good? Mm-hmm. Okay, so let's do these. I think these are on your gift. Correct? Yep. So find the zeros for each function. You're helping me out today. Whoopsie. Nathan.
Okay, so do you have to set x minus 4 equal to 0?
Correct.
So So you get x equals 4.
All right, so this one has 1, 0. What was its, what degree was that, Nathan?
1.
Yeah, degree 1, right? And there was only 1, 0. Right, how about this next one? X squared plus 4, x plus 4. Chris, how are we going to find the zeros here?
I would move, I would take, so, I would do x minus 2 times x minus 2.
So to find the 0, remember, to find zeros, like Nathan was saying, we would set the function equal to 0, right? So in this case, we're going to set the function equal to 0, and when you solved it, you got this, correct? Well, you're about to solve it. So what are you going to get?
It's going to have the zeros of 2 and 2.
All right, x equals 2 and x equals 2. So my zeros here are 2 and 2. What was the degree?
2.
2. How many zeros did we get?
2.
Remember, they could be real, they could be imaginary, they could be repeated, but there's going to be 2 of them. Everybody okay with this? All right, how about letter C? We've got x cubed plus 9x. How are we going to find the zeros there? Casey?
You stack out an x. And then
Okay.
you put, so what you're doing is 0 because you just do x equals 0.
Okay.
Oh, sorry, the parentheses would be x squared plus
X squared plus 9.
Yeah, and then you would do x squared plus 9 equals 0.
Okay.
To get 3, or plus or minus 3i.
Plus or minus 3i. We just talked about that, right? Won't we get plus or minus 3i?
Yeah.
That's the exact same x squared plus 9. Same thing we did right here, right? Okay, so in this case, your zeros, you said, would be 0, 3i, and negative 3i. True?
Yes.
Okay, and what was the degree here, Casey?
3,
And how many zeros did we get?
3.
3. Okay, how about letter D? In this case, we've got x to the 4th minus 16. Veronica, what do you think we were going to do to find the zeros here?
You would do x squared minus 4 times x squared plus 4.
All right, Veronica is noticing that this is a difference of 2 perfect squares. So she is factoring it into x, what was it?
X squared minus 4, and then x squared plus 4.
Do people agree with that?
Yes.
All right, now this guy is also a difference of 2 perfect squares. So what can we write for that one here, Kelly?
7 equals 0, so it's x squared minus 4 equals 0. So you add 4 to one side.
What can we factor it?
Yeah, you could do x minus 2 times x plus 2.
All right, x minus 2 times x plus 2. Can we still have this, x squared plus 4? Can we factor x squared plus 4?
Yeah.
Well, the answer would be no if you're locked into the real number system. Jenna is not locked into the real number system. Jenna, how are you going to factor this?
You're going to set x squared plus 4 equal to 0.
Yeah.
And then you're going to subtract 4 from both sides to get x squared equals negative 4. And then take the square root of both sides. And then x equals 4i and negative 4i. Or 2. 2i and negative
All right,
2i.
because we need the plus or minus, so 2i and a negative 2i. So the factors then would be what, Jenna?
X plus 2i, x minus 2i.
X plus 2i and x minus 2i. Are we okay with this? So overall, we have how many linear factors? 4. What was the degree? How many zeros do we have? 4. So our zeros here, if we're going to list these, are what, Veronica?
It's going to be negative 2 and positive 2, and then negative and positive 2i.
All right, negative 2i and positive 2i. Are we okay with this?
So whenever it's x squared plus a positive number, will we always set it to 0?
You're always going to want to set your quadratic factors equal to 0 and solve it somehow. You can, in this case, there was no x term, right? It was just an x squared term and a constant term. So we were able to, just subtract the number from both sides and take the square root. If it was like x squared plus 2x plus 4, we might have to use quadratic formula for some of these. Okay, let's keep going. Let's talk about the rational zero test. The rational zero test relates possible rational zeros of a polynomial to the leading coefficient and to the constant term of the polynomial. Did I put this rational zero test on your gift?
Yep.
Awesome. So the rational zero test says if the polynomial f of x, and we've seen this before, we have talked about this before. This is just like a way to write a polynomial in general terms. A sub n minus 1, and so on. Those are all the coefficients on the terms, and a sub n would be our leading coefficient. And n is our degree, so I'll have 1x to the n term, then x to the n minus 1 term, all the way down to x to the first, and then really x to the 0, right, for this constant term. Okay? So the rational zeros test says if you've got a polynomial and all of the coefficients are integers, the coefficients have to be integers, no fractions, no decimals or anything like that, then if this polynomial is going to have a rational zero, then it's going to be in this form, p over q. And we're going to talk about the p over q for a minute. But I want to go back to what do we mean by a rational zero. Rational numbers, which we talked about on day 1 back in August, are numbers that can be expressed as a ratio, right? Ratio of integers, right? So like 2 over 5, negative 7 over 3, right? Those are examples of rational numbers. 8 over 1, which is really just 8. So 8 is a rational number, right? Everybody with me? So if we want to find out if a polynomial has rational zeros, we're going to use this rational zero test, right? And the rational zero test basically says if your polynomial function is going to have rational zeros, and it's a big if because there's no guarantees, if it's going to have rational zeros, it's going to come from this list of p over q values, where p is a factor of the constant term, that's this guy right here, and q are going to be all the factors of your leading coefficient, which is this guy here. All right? So, clear as mud, right? Let's take a look at an example of this. So this is on your gift. So we're going to try and find the rational zeros. But I guess before we find the rational zeros, let's say, hey, let's just try and find a list of possible rational zeros first. We're going to make a list, because back in the day, before they had graphing calculators, if you wanted to find zeros of a polynomial function, you couldn't just type in the calculator and graph it and look and see where does it cross the x-axis. You had to apply some various tests to your polynomial. And the rational zero test is one of them. They talk about 3 of them in this section. Unfortunately, I think we're only going to have time for this one test. All right, so in this case, we need to make our list of p over q values. The p values are factors of what? The constant term. So in that case, that's what here, Audrey? What's our constant term? 8, the term without an x, right, is our constant. And so we want the factors of 8. Audrey, what goes into 8? 2 does? 4. How about 1 and 8? 1 and 8. Everybody agree?
Yeah.
But so does negative 1, so does negative 2, and so on. So these are all of our p-values. Those are the factors of our constant term. What about the q values? Those are the factors of what, Tiger? Q's are the factors of the leading coefficient. What's our leading coefficient here? 1 is our leading coefficient. So what number or numbers divide into 1? 1 and negative 1. All right? So we're not going to leave our list like this if we didn't really make a list. We just made like one big fraction. So we want a list, so we're going to have to take every numerator over every denominator. So I want 1 over 1, 2 over 1, 4 over 1, 8 over 1. So I'm just going to write it like this. So how many possible rational zeros do we have? 8. So these are the possible rational zeros. So back in the day, before they had graphing calculators, they would have to test each one of these by hand. What do I mean by hand? How would you test to see if one of these is a zero, Chris?
plug each one into the original polynomial?
Plug them in. Well, how about plugging them in and do synthetic division?
Or that.
All right, so like I could take 1, for example, and then I would take, 1, -5, 2, 2, and 8, do synthetic division, and what would I be hoping to get as my remainder?
0.
0. If I don't get 0 as a remainder, I'm going to reject that. It's not a 0, right? So this is what they would have to do. Now, and you're like, oh my gosh, I got to test 8 numbers? Well, testing 8 numbers is a whole lot better than testing, what? Infinite number of rational numbers. At least this is giving you a finite list to test. Does that make sense?
Yes.
Jenna?
When you're making your list, how come you don't put the positive and negative one underneath? Like, where's that?
I took 1 over 1, and I got
Oh,
so you 2 over 1. I did do that, yes.
okay.
All right, so let's graph this function on our calculators, please. And I want to see, do any of these actually work? Because there's no guarantees. Maybe none of them work. It's very possible that none of them work. But let's see if this function has any rational zeros. And if so, I bet it's going to come from this list.
I have a question.
Yeah.
So because like there's a positive and negative on both the top and the bottom, couldn't you have -1 over 1 and 1 over -1 and those be like a double possibility? Like you could have done a repeated series?
Right, so I mean, we could list them more than once, but since +1 over -1 is going to be the same as -1 over +1, I'm only listing that as, oh, that's a -1.
Okay, but like kind of like when we're solving for the zeros and the equations.
We don't want to list them twice because these are just possible zeros anyway.
Okay.
This is just a list of candidates, all right? Right.
My calculator died.
Thank you for sharing that information with
Say
me.
louder for the video.
What would you like me to do about that, Ryan?
Well, I don't know.
Oh.
Wait, we don't need it for the test. All right, we're fine.
Ryan's calculator time.
I thought
Okay.
this is all we needed for Ryan's calculator.
All right, so let's see. People are graphing these, and I'm going to choose, let's see. Gabby is live presenter. All right, so Gabby, where does it look like your graph is crossing through the x-axis?
-1,
Okay, looks like it's crossing at -1.
2.
Was -1 on our list of possible rational zeros?
Yes, it was.
Interesting. And what else?
2.
2, was 2 on our list?
Yes.
And where else?
4.
Was 4 on our list?
Yes.
Okay, now here's the deal, and this is like my big hint because we got this quiz coming up. But like if I was going to test those, I could put -1 in the box, and then put our numbers, what were they? 1, -5, 2, 8. Do synthetic division, bring down the 1, multiply, add, multiply, add, multiply, add. Did I get a 0?
Yes.
Okay, but then I could test this further and say, hey, what about 2? Does 2 work? I don't have to go back to this. I would use these, right? Hint, hint, hint. So if I do that, and I should have done this on another piece of paper because smartboard because I'm running out of room. But if I did that, I would put 2 in the box and use, where are my numbers? 1, -6, 8. Does that look right?
Yeah.
1, -6, 8. I can get 1, 2, -4, -8, 0. That works, right?
Yeah.
And then look, what's my last remaining factor would be x minus 4, which when I set equal to 0, I get x equals 4, which is what Gabby's telling me she got as her last 0. Does that make sense? Okay, let's try one more of these, and let's take a look at this one. You're going to find the rational zeros for this, but before we do that, we're just going to try and find the list of possible rational zeros. So I need that list of P over Q values. So in this case, the P values are going to be what, Megan?
They're going to be 1, 2, 3, 5, 6, 15, 30.
And 10?
Yeah, I got
All right, we'll squeeze that one in. So these are all of our factors, 10, 15, 30. Don't forget we need the negatives of those also. All right, and what about the Q values? What are those gonna be, Zach? So you need the factors of 2. 2 is our leading coefficient.
So, 1, -1.
And -2. Everybody agree with that?
Yes.
Okay, so this is great, but we still have to make our list. This is not a list. This is just like one big weird fraction. So we need to take every numerator over every denominator. So I'm just going to take everything over the 1 first. So I'll get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. Does that look okay? But now I need to take each of those numbers over the 2. So I need 1 over 2, so I've got to add 1/2 and -1/2 to my list of possible rational zeros. I need 2 over 2, but that's 1. I already have that in the list. I don't need to write it again. I need 3 over 2, so I got to list plus or minus 3 over 2. I need 5 over 2. I need 6 over 2, but that's 3. I already have that. I need 10 over 2, that's 5, I already have that. I need 15 over 2, I don't have that one, I gotta squeeze that one in. And I need 30 over 2, but that's 15, I already have that. So what do I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2. I've got 24 possible numbers that before the graphing calculator, I would have to check 24 synthetic divisions, right, and see if any of them work. If none of them work, then I would know for sure that this polynomial has no rational zeros. And I could stop looking. I wouldn't have to try 5 over 9. I wouldn't have to try -7 over 3. Right? I wouldn't have to test any of those. Because if it's going to have rational zeros, it's coming from this list. Get it?
How do we do synthetic division of fractions like the same way?
Same way. Same way. So go ahead and graph this, please, on your calculators.
Doing it with 24.
Pardon me?
Synthetic division with 24 things, having none of them be right, that'd be awful.
Well, no, that would be great. So you're like, just got no rational zeros. I'm done. My work here is done. Okay, let's see. Who are we? Casey, is this yours graphed? All good?
That's good, Casey.
Yeah, Casey.
Okay, on this, Casey, I mean, we're not seeing a whole lot of this graph, but we are seeing, okay, yeah, that's fine, but you know what, I don't want you to mess with the, no, what happened? I thought you were doing this.
Oh,
Casey.
Go ahead. Oh, I said don't mess with it. Go ahead and window zoom, but don't mess with the X min, X max. But can you make the Y min like, I don't know, like -1,000?
Oh, wow.
And Y max 1,000? I'm just making this up. Hey, that's not bad. Okay, so what are we noticing? It's a degree 4. Here's our leading coefficient test. Right? And it looks like it's crossing through where, Casey? Like where on our x-axis is the graph crossing?
At -3, it looks
All right,
like.
stop. Is -3 on our list?
Yes.
Okay, where else does it look like it's crossing?
It's like about 1/2, that's it.
Oh, it could be 1/2. Is 1/2 on our list?
Yes.
Yes. What else?
Looks like it's about 3 for that one.
3 is over here.
About maybe 2.
2 maybe? Is 2 on our list?
Yes.
Okay, and what else?
5.
Is 5 on our list?
Yes.
Okay, so, but here's the thing. And we could test this and say, oh, let's try -3 in the box, see if we get a 0 and so on. Here's the big point that I want to make, is that once you find one rational zero and you do synthetic division, maybe the other 2 zeros, let's say if it's a degree 3, maybe the other 2 zeros are going to end up not being rational, but they might still be real numbers. In other words, you're still going to see the graph crossing through the x-axis, but it doesn't hit at rational numbers, so you would have to do quadratic formula to find those irrational zeros, and it might turn out to be like 2 plus 9i or 2 minus 9i. That's the other thing, they always come in conjugate pairs if they are irrational zeros, okay? Or you'll see a degree 3 like this, for example. It's a degree 3, right? This thing, right? And it looks like it's crossing through how many places? So that means it's got one real zero, but how many zeros is it guaranteed to have?
2 or 3, 2 more on it.
2 more, 3 altogether. So what are the, so if it's only crossing through one time, what happened to the other 2 zeros that we're guaranteed to have? They must be imaginary, right? Does that make sense?
Yeah.
And how would you find them? You would do synthetic division with this one. Let's say, oh, this one happens to cross through at -6 or something. You would do synthetic division with -6, end up getting a 0 here. And since this was a degree 3, when you do synthetic division, you're going to end up with a quadratic, a degree 2 here. And then you try and factor it, but if it doesn't factor, you do quadratic formula. Does that make sense?
Yeah.
Oh, yeah.
Which,
Do
okay.
you understand?
All right.
I understand. Do you understand?
I think I'm done talking.
Yes, I
All right,
do.
so
I
I'm going to stop this video, but there may be a little video for you to watch.
Can we say-
Um,